Hey guys, this is going to be the homework for 4.4 and 4.5, although you probably are already done with this because this is what we did in class. But for those that might have missed, or if you want to just redo a problem that you didn't really quite understand, hopefully you'll get some help in this video. So this first one, we're talking about Boyle's law, and Boyle's law states that if the temperature of an ideal gas is held constant, then the pressure P of the gas and its volume V satisfy the relationship such that P is equal to K over V, where K is constant. Which of the following best describes the relationship between the rate of change with respect to time of the pressure and the rate of change with respect to time to volume? So you can see all these right here. We have the change of the pressure with respect to time, and on the right side we have change of volume with respect to time, but which of these is correct? So we're going to take the formula that we have, we're going to take the derivative with respect to time, and that's going to be equal to, well, I guess before I do that, I'm going to rewrite the equation to be P is equal to K times by V to the negative 1. Remember that K is constant, so we're going to use the constant multiple along with the power rule here. So I can bring the negative down. That's going to be negative K V to the negative 2 times by dV dt. So this is implicit differentiation because we're taking the derivative of V, which is a function of time. Okay, and so if I just kind of do some algebra, this is equal to negative K over V squared times by dV dt. So that would be D right there. Okay, a right triangle has base x feet and height h feet, where K is constant and h changes with respect to time. Measured in seconds, the angle theta, measured in radians, is defined by tangent of theta is equal to h over x. Which of the following best describes the relationship between d theta dt and the rate of change of theta with respect to time, and dh dt, the rate of change of h with respect to time? So we have the formula again here. In the triangle, the base stays the same while the angle is changing, and so is the height. So I guess if you think about this triangle right here, we'll call this the height, we'll call this x right here, and then we have this triangle right here, and you can see that this angle right here changes with respect to time, and so does h. Okay, and so but you can always see that the base is what remains constant, so we have to treat that as such. So I'm gonna take this right here. Now, I'm not going to take the derivative right away because the derivative of tangent is secant squared, and I'm just kind of looking at my answers right here, but there's no secant squared, but I do see stuff like x squared plus h squared and the square root of x squared plus h squared. So I'm seeing this stuff right here, which makes me think that what they're doing first is they're doing tangent inverse, because this looks more like a trig, an arc trig derivative. So if I do tangent inverse to both sides, I get theta is equal to tangent inverse of h over x. Okay, and now we're going to go ahead and take the derivative. So we'll call it d theta dt on the left is equal to the derivative of tangent inverse is 1 over 1 plus h over x squared. And then we're going to multiply by the derivative of the inside. Now, because x is constant, I'm really just taking the derivative of h and multiplying by 1 over x. So the derivative of h is, so I'll say 1 over x because that's constant, times by dh dt. Okay, so this was just the derivative of h over x. And then for the rest of this, we're just going to do some algebraic manipulation to kind of get what we need. But this is, so I'm going to rewrite this denominator here as this, I'm going to call as x squared over x squared, because that is what 1 is. And then I'm going to call this h squared over x squared. And then you can see that I have a common denominator if I write it like this. And so I'm going to write it as x squared plus h squared over x squared. For this right here, I can do like a keep, change, and a flip. So then I'm going to get x squared over x squared plus h squared times by 1 over x times by dh dt. And then that will cancel with the power right there. So it's going to be equal to x over x squared plus h squared times by dh dt. And so that should just be A, I believe. Yeah. Okay. Let x and y be functions of time such that the sum of x and y are constant. Which of the following equations describes the relationship between the rate of change of x with respect to time and the rate of change of y with respect to time? So we're going to make a function out of this right here. So x and y are functions of time such that the sum of x and y is constant. So that means the sum of x and y is equal to some constant. We'll call it k. It doesn't really matter, but I think they use k. You can kind of see in here. Now, because that's constant, it's not a function of time, unlike x and y, which are functions of time. Okay, so let's take the derivative of this. We're going to take the derivative of x, which would just be dx dt, plus the derivative of y, which is dy dt, and that's going to be equal to 0. And then I'm going to subtract this term. So we'll say dx dt is equal to negative dy dt. And so that's got to be b right there. Okay, now we're getting into some story problems here. We'll have about 2 of those, so this one and then there's one more. But so it says a tube is being stretched while maintaining its cylindrical shape. The height is increasing at a rate of 2 millimeters per second. At the instant that the radius of the tube is 6 millimeters, the volume is increasing at a rate of 96 pi cubic millimeters per second. Now, this right here, at the instant that the radius of the tube is 6 millimeters, so this right here, it's not too explicit, but that is indicating that the radius is also changing. So the height, the radius, and the volume are all changing with respect to time. Okay, which of the following statements about the surface area of the tube is true at that instant? So you can see that we're looking for surface area increasing or decreasing. So we're looking for the rate of change of surface area. Now, it gives us 2 equations here, so S and V. S for surface area, V for volume. So I'm going to go ahead and just start with this. And the reason why I want to start with this is because, well, we're trying to look for the surface area, the rate of the change of the surface area. And so sometimes it's kind of good to kind of just start by going after what the question is asking for. Oftentimes, though, you're going to see that you're going to run into some issues. But as long as you start by doing that, it kind of just gives you direction as to what you should always be looking for. So I'll show you what I mean. So we're going to take the derivative of this surface area part. I'm going to split it up into 2 parts because this is going to require the product rule because r and h are functions of time. And so we'll say s prime is equal to the first times by the derivative of the second plus the derivative of the first, which would be 2 pi r prime times by the second. Okay, so here it is. This is exactly what I'm trying to find, and I'm going to try and plug in some values that I have. So I know that r, we're going to put in 6 for r. So s prime is going to be equal to, well, this is 6, and the rate of change of the height is 2. So 2 times 6 times by 2, that's going to be 4 times by 6, so 24 pi. Plus, now here, I don't know what the rate of change of r, and I don't know what the height is going to be at that instant. And so this right here is just going to have to remain 2 pi r prime times by h. And so I'm left with this. I'm trying to figure this out, but I do not know what r prime is, and I don't know what h is. So now I'm going to have to look elsewhere, figure out what I need in order to help me finish this problem right here. But this is what's important right now here. This is what I don't have. This is the information that I need. So going back to what I've been given, I've also been given that volume is increasing at 96 pi cubic millimeters per second. So I know dV dt is equal to 96 pi, and then the milliliters cubed per second. Okay, now I have an equation for volume, but I don't know what volume is, and I don't know what height is. So this equation right here is not too helpful because, again, it kind of gives me two unknown variables. I don't know what volume is because I don't know what the height is. And so what would better help me is if I had a formula that used dV dt. So let's go ahead and take the derivative of this, because then I can use that value. So dV dt, again, I'm going to need to use the product rule. So it's going to be the first times by dH dt plus the derivative of the first, which would be 2 pi r dr dt, times by, man, I need to be more consistent. Times by h. I'm going to go back over here and change this to dr dt. So dr dt times by h. Okay. So now let's go ahead and plug in values that I know. So I know 96 pi is going to go here. So 96 pi is going to be equal to, I know that r is 6. I know that dH dt is 2. So this is 36 times by 2. So that's going to be 72 pi. Plus 2, do I know anything here? I know that the radius is 6. So 2 times 6 would give me 12 pi. But I still have dr dt times by h here, just like what I had before over here. So these are things that I don't know. But the difference here is that I have two unknown parts right here, but I could solve for this part right here by getting rid of these terms. So I could subtract 72 pi here. So subtract 72 pi, and that's going to give me 24 pi, which is equal to 12 pi dr dt times by the height. And I could divide by 12 pi, which would give me 2 is equal to dr dt times by h. So now I actually have a value that I can substitute for the whole thing of dr dt times by h. So I can replace that here. So s prime is equal to 24 pi plus 2 pi times by 2. So that's going to be equal to 28 pi. And it is positive, so therefore we have to be increasing. So it's got to be A. So this is what I mean. We're looking for s prime, so start with that. We kind of ran into a problem here, so we look to other information that I have to try and figure out something that I'm missing, okay? We're going to use that kind of thought process in another problem here in just a bit. So for 5, we have a particle that moves along a hyperbola. xy is equal to 18. For time t is greater than or equal to 0 seconds. At a certain instant, y is equal to 6. The rate of change of y is equal to h. Which of the following is true about x at this instant? So x is decreasing or increasing, so we can basically already tell dx dt is what we're looking for. So let's go ahead and just take the derivative of this right here, keeping in mind that x and y are functions of time. So we're going to use the product rule. So we'll do the first times by the derivative of the second, plus the derivative of the first times by the second is equal to 0. So I took the derivative. I'm looking for dx dt. So I know that y is 6. I know that dy dt is 8. x I can find by plugging in 6 to this equation right here. So x times by 6 is equal to 18. That means x is going to be equal to 18 over 6, which is going to be 3. So I get 3 times by 8 plus dx dt times by 6 equal to 0. Move that over there. So I have dx dt times by 6 is equal to negative 24. Divide by 6, so dx dt is equal to negative 4. And that's going to be units per second. And so that just means that x is decreasing by 4 units per second. Okay, the figure above shows a Ferris wheel with a radius of 5 meters as Jalen, whose eye level is at 0.02. So the eye level is at, this is 2 units up, and it watches a friend on the ride in one of the cars as the wheel turns. So that's that right there. And this point right here is at that instant, it's going to be 12.7. But remember that x and y is changing. X and y is changing around here, right? Okay. But at the instant 12.7. And the position, car, x, y. If x and y are functions of time, meaning that these are changing with respect to time, what is the rate of change of z? So z would be this distance right here when x is equal to 15 and y is equal to 11. Oops, so that's not right there. That's 15 and 11. This center, 12.7. That's that right there. And so x equals 15, y equals 11, and dx dt is equal to 1. The equation of the circle with a radius is given here. Okay, so this will come into play, but again, we're going to use the thought process that we used up here. What is it that we're trying to find? We're trying to find the rate of change of the line of sight right here. So this is z. Okay, so this is z. We're trying to find the derivative, the rate at which this distance is changing as the wheel turns. Okay, now we can make a triangle from this right here. Obviously, we can make the triangle from there to there. We can make the triangle go from here to here. Okay, this distance right here we know is x. So this distance is x. We know this distance is z. This distance right here is going to be y minus 2 because the distance from here to here is y, but we have to account for the units here. So that's 2, so y minus 2 for that right there. And then we need a formula that's going to relate all these together. So we're going to say z squared is equal to x squared plus y minus 2 squared. And so we're going to take the derivative of this equation right here because we're trying to find z prime. So that's going to be 2z prime equal to 2x x prime plus 2y minus 2 y prime. Okay, and let's go ahead and see what values I can plug in. So I know that this is going to be, we're going to measure the rate of change when x and y are these values right here. Now, one thing I'm going to note is that the 2's aren't necessary because we can divide them all out. What is z though? So z is going to be the distance from here to here. X is going to be 15. Y is 11, which would make this distance right here 9. And so z is going to be equal to the square root of 15 squared plus 9 squared, which if you do that, that's going to be equal to the square root of 306. Okay. So this is going to be the square root of 306 times by z prime equal to x, which was 15, and x prime, which is 1. So this will just be 15, okay, plus 9, because if I plug in 11 here, that's going to be 9y prime. I don't know what y prime is, but I do know z prime is going to be equal to 15 plus 9y prime over the square root of 306. Okay, now, so kind of like the same thing that happened up here in this problem, I know I'm looking for this, but as I am looking for that, I come up with the other unknown rate that or variable that I don't know. So now I have to look elsewhere for that right there. They gave us another equation, and they gave us the fact that there's another thing happening here, not just the rate of change of this distance right here, but the rate of change of the position is also changing because the wheel is turning, right? And so that's why this formula is going to be helpful to us. So I have this right here that I'm going to take the derivative of, but I'm first going to plug in the center point. So this is 12 and that's 7. And this right here is going to be 25 since the radius is 5. So I have x minus 12 squared plus y minus 7 squared equal to 25. Now, as I take the derivative of this right here, I'm going to get x prime, I'm going to get y prime, and then that will be 0. But so what I'm looking from this is y prime because that's what I need to help finish this one over here, right? So take the derivative. This becomes 2x minus 12 times by the derivative of the inside, which is x prime, plus 2y minus 7 times by y prime, the derivative of the inside. That's going to be equal to 0. And so we're going to use this, and keep in mind that we're using this at the instant that x is equal to 15 and y is equal to 11. So this right here, well, again, the 2's don't matter because those are going to cancel out. So we're going to plug in 15 for x. So 15 minus 12 is 3, and x prime, again, is 1. And then we're going to do plus, so we're plugging in 7, no, we're plugging in, what was the y value? We're plugging in 11 for y. So 11 minus 7, that's going to be 4, y prime equal to 0. So 4y prime is equal to negative 3, and y prime is equal to negative 3 over 4. So that is what we're going to use for y prime. So y prime is going to go right there. And then, so z prime is going to be equal to 15 plus 9 times by negative 3 over 4, all over the square root of 306. And there we go. We'll punch that in. Now, whenever you do punch that in, I wouldn't pay too much attention to what's happening here, because you might not get the same exact expression that you have over here, but you'll get one of these right here, meaning that this expression is equivalent to one of these three, but it definitely doesn't look like it, and you'd have to use some algebraic manipulation, but that's kind of irrelevant because we have a calculator, and so we're looking for these values right here. So if you do the math right here in your calculator, you should get 0.47, so it's either going to be A or C. So is the cart moving towards or away? Now, I think it would be away. So if I think about this distance right here, if it's coming closer, that means the distance of z, this distance would have to shrink, right? So as I compare it to, like, maybe if it went, as this turns here, z would be shorter than, let's say, than if it were at this point right here. So it doesn't really specify, which is unfortunate, which way is positive, which way is negative, but I'm going to, because, I mean, yeah, it just really depends. Eventually, this is going to be shorter, but I think as it's right here, z is going to first start by increasing if it goes away, so as it turns away. So increasing would mean that this is positive, which is what we got. We got a positive 0.47. And so I think that means it's moving away, because that means that this would be increasing, which is why we got positive. So it's going to be C. Okay, and this last problem. Okay, so a sculptor uses a constant volume modeling clay. So a sculptor uses a constant volume. So volume is constant of clay to form a cylinder with a large height and relatively small radius. The clay is modeled in such a way that the height of the clay increases and the radius decreases, but they increase and decrease in such a way that the volume remains constant, but it remains its cylindrical shape. At time t equals c, the height of the clay is 8 inches. So we're going to say h is going to be equal to 8, and the radius of the clay is going to be equal to 3. And the radius of the clay, so I'm going to say dr dt, is equal to -1/2 inch per minute. And this is all inches. Okay. All right. At time t equals c, at what rate is the area of the circular cross sections of the clay decreasing with respect to time? So, area of a cross section of a cylinder, so area is going to be equal to pi r squared, right? So we're going to take the derivative of these with respect to time. So dA dt is going to be equal to 2 pi r times by dr dt. And then we're going to plug in values. So it's going to be equal to 2 pi. The radius is going to be 3. And the rate of change is -1/2. And that's going to turn out to be -3 pi inches squared per minute. Okay. For B, at time t equals c, at what rate is the height of the clay increasing with respect to time? So we're going to use the volume. Yep. So volume, show the computation. So let's take the derivative of this. So we're going to say, well, remember that volume is constant in this case. So when I take the derivative of that, it's going to be 0. And we're going to need the product rule here. So we'll take the first part, times by dh dt, plus the derivative, which is 2 pi r dr dt, times by h, okay? And then let's plug in some values. So we have 0 is equal to, r is equal to 3, h prime is what we are looking for, right? At what rate is, yeah. So that's going to be 9 pi times by dh dt, plus the height is equal to 8, r is equal to 3, so that's going to be 24 times by 2, so is that 48 pi? So 48 pi times by -1/2. Am I doing this all right? I think so. So in any case, that's going to be 0 is equal to 9 pi dh dt minus 24 pi. And then I'm going to add 24, so I get 24 pi is equal to 9 pi dh dt, divide by 9 pi, and so dh dt is equal to 24 pi over 9 pi, which is going to be equal to, both of those are divisible by 3, that'd be 8 over 3, and that's going to be inches per minute. Okay. And then for the last part, which will be C. Write an expression for the rate of change of the radius of the clay with respect to its height. So that means right here, the radius of the clay, the rate of change of the radius of the clay with respect, that is dr dh. Okay. This part right here is going to be a little less intuitive. But so we're trying to relate dr and dh together. Now, this is going to require dr dt and dh dt, and we already have an expression that uses dh and dt and dr and dt. So we're going to use this same exact equation that we have right here. Okay. So let's go with this right here. Now, something that's not super intuitive is the fact that something that I can do to manipulate this formula is if I take dr dt, if I divide dr dt by dh dt, this is going to result in dr dh, which is exactly what I'm looking for, right? Yeah, because if I do like a keep, change, flip algebraic manipulation, that turns into dr dh because the dt's will cancel. And so something I'm going to do with this formula is I'm going to divide all three of these parts by dh dt. That's just going to be 0. So as I do that, I'm going to get 0 is equal to, those are going to cancel, and I'm going to be left with pi r squared. Plus, now again, if I divide these together, my result is dr dh. So I'm going to get 2 pi r times by dr dh times by h. And then all I have to do is solve for this part right here, and I'll have my answer. So I'm going to subtract that over there. Well, also one thing to note, pi isn't going to matter, and you can get rid of the r's as well because you can divide those out. So then I'm going to subtract r over, so negative r is going to be equal to 2h times by dr dh, and then divide, so then I get dr dh is equal to negative r over 2h, and that's what I get right there. So, and then what is it? Okay, so write an expression for this in terms of h and r. There we go. Okay, so that's this homework assignment.